Hello everyone. Today we are going to talk about what is cluttering. Cluttering is a very popular technique in unsupervised learning. Before we have studied supervised learning, so let's recall that what I mean by supervised learning and counter it with unsupervised learning. So supervised learning. So the word supervised refers to the fact that there is a target, a label that we are trying to predict from training data X. In contrast, unsupervised learning, there's no labels Y. So there's no Y. We only have the features X. And we want to know how the features relate to each other. So in particular, what are the goals of unsupervised learning? So first of all, they are not as clear as supervised learning. For supervised learning, the object is to predict y from x. But now we don't have a y, so the objective is a little more fuzzy. For example, we might want to discover subgroups among the observations, or we might want to know, is there a good way to view the data? So we are going to discuss, there are lots of methods for unsupervised learning. But in this short lecture, we are just going to talk about cluttering. So the method cluttering refers to a broad set of techniques for finding subgroups or clusters in datasets. So we are trying to segment or partition the data into subgroups that are similar to each other. And we'll have to define what we mean by similar or different in order to do the partitioning. And in a lot of cases, the way we decide to cluster, the way we decide on what's similar or different, depends on the context. So clustering looks for homogeneous subgroups of the observations. So it is looking for similarity among observations. For example, suppose we collect P measurements on each of n breast cancer patients. There might be different unknown types of cancer which we could discover by clustering the data. Now we are going to talk about two clustering methods. Two main clustering methods are k-means clustering and hierarchical clustering. That are two most important methods. In k-means clustering, we'll predefine k. K is the number of clusters. And then we will see there is a way of grouping the observations into k groups. And then, of course, we'll have to define what k is, what this number of subgroup is. And that's going to be an important and difficult choice. The second method is called hierarchical clustering. For hierarchical clustering, we don't pre-specify the number of clusters k, but rather we group the data in all number of clusters. So this is done in a hierarchical fashion. Hierarchical clustering is very interesting, but for the limit of time, today we focus on k-means clustering. So let's talk about the simplest method, k-means clustering. So before we describe it, let's see an example of the result of k-means clustering. And this is some simulated data. And there are two features. And there's a group on the top, some space in between, and a group at the bottom. And now we apply k-means clustering, and we have pre-specified k. For this dataset, we can specify k to be 2, 3, or 4, and then we run the clustering out of it. It will produce the groups indicated by different colors. If we specify k equal to 3, it would be forced to find 3 groups, and the 3 groups k-means clustering found out are indicated here by 3 different colors: green, blue, and gold. So what k-means clustering has done is it's broken up this apparently homogeneous cluster into 3 clusters. So you can see that the effect of k-means clustering is really important, because if you choose k to be large, it's going to be forced to break up groups like this one. Like, for example, if we choose k equal to 4, it is going to be forced to break up groups which are fairly homogeneous. So you can see the effect of k is really important, because if you choose k to be very large, for example k equal to 4, it is going to be forced to break up groups like this one, like the third plot, which is fairly homogeneous. Now let's actually look at the details of k-means clustering. Firstly, we have to define some notation for clusters or sets. So we'll call them C1 through Ck, and they are sets of indices of the observations. So the indices are 1 through n. Those are our observations. Each of these C's is going to be a subset of 1 through n, and the subset is going to be a partition of 1 through n. Now, as we want to get formalistic, we'll say the union of C's is 1 through n. So if we can count them all together, they make up 1 through n. So they are a partition of 1 through n, and there's no intersection. So there's no overlap between the clusters. So this is just a fancy way of saying we are going to break up the points 1 through n and do k groups, which are not overlapping and cover the whole set. And again, if the ith observation is in the kth cluster, then I will be a member of the indices for group k. So again, we want to somehow find the partition C1 through Ck, which is a good clustering. Now there's a question. So you may ask me, what do you mean by group clustering? So k-means clustering defines good clustering to be one in which the within variation is small. So getting back to this picture. So getting back to this picture, if you ask me, divide this into 3 groups. Okay, I'm going to find 3 groups so that within each group, like within the gold group, the variation is small within the group, so that the points are close together. So similarly for the other two groups, so the points in the group are close together. So it is a very intuitive definition. For example, we can use square distance in two directions for k-means clustering, and we want to find the partition C1 through Ck to minimize the total within cluster variation. So we are going to assign the end data points to k clusters. The total within cluster variation summed up over k clusters is as small as possible. We normally define within cluster variation to be the Euclidean distance, the pairwise squared distance between each pair of observations in the cluster. Add it up over the p features. So this is in the Euclidean or squared distance between observations I and I prime. And we sum it up over all I prime in the cluster. So this is the total pairwise between every pair in the clusters Ck. And we are going to minimize the total of this over K, the total variation over all clusters, and here it is. So here's our formula. Here's our optimization objective function. Here's the within cluster variation, and we are going to find the clustering C1 through Ck that minimize that. So we have a criteria. But let's actually talk about the k-means algorithm, and then we'll circle back and see why I minimize the objective function, why I minimize the within cluster variation. So how k-means clustering works? So you can see from the name, for k-means clustering, there are two words in k-means clustering, of course. First word is k, second word is means. So what means mean? So it's going to use a mean somehow. So it is actually an alternating algorithm that first of all, we assign to each observational cluster from 1 to k. So here, this is the k. K is fixed. We have to decide ahead of time. I'm going to pick k equal to 2, 3, 4, or whatever number. So each observation is assigned to a cluster 1 through k, and then we have two steps, which we alternate back and forth. For each of the k clusters, on the one hand, we compute the centroid. That's the average value for each feature of all the points in the cluster. It is the mean in the vertical and horizontal direction of the points in that cluster. So having computed the centroids for each of the clusters, on the other step, we assign each data point to the closest centroid. And then having done that, we have a new set of cluster assignments, C1 to Ck. We go back and we compute new centroids. With these new centroids, we complete our new assignments, and we alternate back and forth until hopefully these things settles down. And the solution is the k-means clustering. The solution we want is the assignment of points to the groups. Now we look at one example. So here's an example. This is our data. It is unlabeled data. And now we fix k to be 3. So in the first step, we are going to assign points at random to clusters. So we have indicated this by the colors. The color doesn't matter. The purpose of different color is to distinguish different clusters. And you see the grouping is not very good yet. So now the first step is to compute the centroids. So these are the advantage of these are the average of the horizontal and vertical direction of all the points in different clusters. And here the centroids are pretty much on top of each other. They are overlapping. The reason is that the assignment, the initial assignment was random, so there's no real grouping yet. But don't worry. So the k-means clustering will work its way to a good solution eventually. So now we take the centroids and we find the closest point to each of the centroids. So at each point we ask, are you closest to which centroid? So are you closest to green, purple, or orange centroid? And now we color the points accordingly. That is, we assign points to closest cluster center. So this is the partitioning step. So even though those first 3 centroids were overlapping, they weren't exactly, and so that we define a fairly nice partition of the data already. It is an almost good job. And then, given this new assignment, we find the centroids again. By now, the centroids are going to move a lot now. Now the centroids are sitting really right in the middle of the clusters. And the algorithm we are going to continue, and we need to make several refinements. And here is the final k-means solution for this example. So k-means clustering algorithm is very intuitive. Now let's go back. You may ask me why this algorithm converge. That is why this algorithm minimize the total within cluster variation. So the reason is you can write the pairwise variation as the variation around the component-wise means. So this is the key to k-means clustering. So let me write down the formula and then you think about it. So we really didn't care about the centroids. All we care about was the clustering. What k-means clustering has done is it has changed this to an equivalent expression involving the centroid. And each of those steps is going to decrease this criterion. So if you have centroids, then when you come to update the assignments of each point, it is going to go to the group for which this distance is smallest for fixed centroids. And on the other hand, if all the assignments are fixed, we know that the sample mean minimize the sum of squares, and so that's why each of those steps necessarily make the criterion go down. That's why the algorithm converge, to the minimal point of the objective function, to the minimal point of the within collector variation. Now there are some problems with k-means clustering. The k-means algorithm can get stuck in local optimums. So can you tell me the reason? The reason is that, so first let me tell you what I mean by local optimum. Local minimum, in calculus, it means that the derivative of the function is 0, but it is not the lowest point of the function. So if a function is not convex, you can have a place where the derivative, or there's a value which is flat, but it is not the lowest value in the whole function. So this algorithm will get to a local minimum. It will get to a value of the function we are trying to minimize, but it won't be the lowest value necessary. So we can think of this function that we are trying to optimize as being like a big value, but it has got lots of little sub-values or little points or whatever, and any minimum is one of those, and we can get stuck in one of those. So this is because the objective function, the total within collector variation of k-means clustering, is non-convex. In other words, it can go up and down and have more than one value, and the k-means algorithm will land you in a value, but not necessarily the lowest value, because the function is not convex. So actually, here's an example. So if this is for the same data, here's an example where we start the algorithm from 6 different starting configurations. So remember, a starting configuration was we assigned each point at random to one of the collectors. And this is actually a good thing to do with k-means clustering, since we are not guaranteed to get the global minimum. We start the algorithm at more than one place, and we just examine the value of the criterion at the end in each case. Remember that starting the algorithm was this random assignment of points to the number of clusters we are using. So we start the algorithm from different places. We get actually quite different solutions. Some are bad solutions because you can see the number above the plot is the within collector variation, the final within collector variation, which is not a small number. Okay, so the first plot gives us a bad solution. So typically we pick the lowest value. It looks like we get 3 different solutions. So, but actually they are the same, only the color is different. So they are actually all the same. The coloring are different, but the coloring is arbitrary. So these 4 panels, give us the good solution. But the top left and the bottom right are actually bad solutions again.